ಕಂದ ಹೇಳ್ತೀನಾ?
We studied about quantization process and we saw the graph for mid-trend and mid-rise type of quantization, sir.
Okay.
We studied about quantization, noise and plotting graph versus time versus magnitude. We studied the error that is being formed. Q
When
equals
the quantization. Okay.
minus
What is the
delta.
maximum error? Quantization error?
Sir, it is from minus delta by 2 to delta by 2, sir.
Means we say it is plus or minus delta by 2.
Delta by 2.
Yeah, plus or minus delta by 2 is the maximum quantization error, what we can say, where delta is the step size. Okay.
Yes.
Okay, good. At least you remembered. No, you're not saying you're not remembered anything. Okay. So, what about Arshita? Arshita. Yes, I'm not able to hear you, Arshita. Are you speaking? Unmute ಮಾಡಿದ್ದೀರಾ?
Yes, sir.
Yeah, can you just say what is quantization? How do you define quantization? Yes, no definition for quantization. What about Nagaveni? Nagaveni. See, people should respond, I am saying. Ashwini. Ashwini. No. Bharti. Yes, Bharti. No, Bharti. Yes, Dhanya. Dhanya. What about Chandana?
Yes, sir.
Yeah, can you define quantization?
It is the process of mapping infinite values to a set of finite values, sir.
Of what? Amplitude or? Yes, you got my point. You need to tell with respect to discretization of the amplitude of the sample signal, right?
Yes, sir.
So when
It's
I
regarding amplitude only.
yeah, so when I sample it, it will be discretized in time, right? But still its amplitude is continuous. So to make it discrete, I go for the quantization process. Okay. Yeah. Okay, let me continue with the task what I have discussed yesterday. Yeah, just as a recap from my side, I say two fundamental processes involved in the generation of digital pulse representation of an analog signal are what? Sampling and quantization. I said the sampling process takes care of discrete time representation of the message signal, and the quantization process takes care of the discrete amplitude representation of the message signal. Okay. So the combined use of sampling and quantization permits the transmission of the message signal in the coded form. So this is what the example of sampling and as well as quantization. See, first one is what the example of sampling, and second one is the example of quantization. How do we do the quantization of the samples, right? Then, yeah, this is one more example I have taken to show how signal is sampled and quantized. Then, yes, I was telling about this human sense, right? Here and I are the receivers, and it can detect only finite intensity differences. So with that, I was telling finite amplitude ranges of the signal. You find an infinite number of amplitude levels, right? Okay. Yeah, I was told about this amplitude quantization is defined as the process of transforming the sample amplitude, that is m of nts of a message signal m of t at a time t is equal to n into ts into a discrete amplitude which is denoted as v of n into ts taken from a finite set of possible amplitudes, right? And here we assume the quantization process is a memoryless and instantaneous, okay, which means that the transformation at a time t is equal to nts is not affected by earlier or later samples of the message signal. Okay, so whatever like Ananta, what he was telling, he has not remembered. Similar to this, so this will means it will not depend on yesterday's or tomorrow's this one. So it depends only on the present day this one. Okay. Uh, yeah, I told about this process. It means to simplify the notation, we drop the time index exit, right? Instead of writing m of n into ts, just I write m is a my continuous signal sample. Then I pass it through a quantizer. There I used to write g of nts instead of writing that just g of some function. Then output of that quantizer will be a discrete sample. I represent it as v just. Okay. Yeah. Uh, fine. So here I said mk plus 1, mk plus 2, and so on. No? So where k is the k value can range from 1 to L. So L is the what? We say the total number of amplitude levels used in the quantizer. Right? So the amplitude mk, where k is 1 to L, are what? The decision levels or decision thresholds we say. Okay. Fine. This is all about how we represent output of the quantizer and all. Just I said output of the quantizer is represented as what? V of k, right? Uh, and I said what is step size also, right? So the spacing between two adjacent representation levels is known as the step size. Yeah, so I can write V, that is output of the quantizer, as what? G of M, where G is the quantizer function, M is the input signal, right? Usually it will be of staircase type. And I was told that there are two different types of quantizers. One is uniform quantizer and another one is non-uniform quantizer. So in case of uniform quantizer, the representation levels are uniformly spaced. Okay, the representation levels are uniformly spaced. In case of non-uniform quantizer, the representation levels are non-uniformly spaced, right? So the quantizer can be characterized in terms of mid-red type or mid-rise type, right? So in case of mid-red type, I said the origin lies in the middle of the thread of the staircase, okay? And in case of mid-rise type, the origin lies in the middle of the rising part of the staircase. Okay, so these are the two graphs which I have shown. So this is of a mid-red type, right? Here the middle of the thread is lies at the origin, right? That is what is called mid-red type. And here these are the decision levels, right? It will be what, delta by 2, 3 delta by 2, 5 delta by 2, and so on the x-axis. And y-axis it will be what? Delta, 2 delta, 3 delta, 4 delta, and so on. Positive y-axis. And similarly on negative axis will be minus delta, minus 2 delta, minus 3 delta, minus 4 delta, and so on. Okay. So in case of mid-rise type, I said the origin lies at the middle of the rise of this staircase waveform, right? So here the x-axis means the input level, the decision levels are what? Delta, 2 delta, 3 delta, 4 delta, and so on. And y-axis it will be delta by 2, 3 delta by 2, 5 delta by 2, 7 delta by 2, and so on. Okay. Yes, sir. While doing quantization, I said there will be a error. Means the quantization process introduces an error. So which is what the difference between input signal and the output signal, right? So that is known as the quantization noise. So yeah, this is one diagram where I have shown what will be the quantization error. So this dashed line is my input signal, and this staircase waveform is my quantizer signal, and whatever the red color this waveform I have shown, this is my error. Okay, so the maximum error will be, I said it is plus or minus delta by 2. Yeah, so another diagram which shows the quantization process and as well as the error, right? So this is my input signal, dashed signal, and this staircase waveform is my quantizer signal, right? So if I take the difference between input signal and the output signal, that will be my error, quantization error, right? It may be either plus delta by 2 or it may be minus delta by 2. Yeah, one more diagram I have shown with the different colors, right? Input signal, then quantizer signal, then what will be the error. Yes, one more which still gives better representation of that error and as well as the threshold values, right? So decision levels, I said for mid-rate type, delta to delta, these are the things, and here also y-axis I have written delta to delta, but here this is the decision level, okay, delta by 2, p delta by 2 and so on, okay? And these are the different levels. So we code that by these levels by using a binary number. I will come back to that while discussing about the PCM. Okay, so we were doing this mathematical expression for finding what is the quantization noise and all, right? So to begin with, I said input to the quantizer is my input signal, right? And which I represented as M, okay? And this sample will have a zero mean, and we represent the random variable by capital M, right? So sample value will be represented by a small alphabet, that is M, and its a random variable is represented by a capital alphabet, that is M, okay? So if this input has a non-zero mean, and we can always remove this by subtracting the mean from the input and then adding it back after the quantization. Okay, so then the quantizer will map the input to random variable of a continuous amplitude into discrete random variable, which we denoted by capital V, right? And its sample value will be small v. Okay, so sample value of the message signal is small m. Similarly, the sample value of the output of the quantizer is small v. So the quantization error, which is denoted by the random variable by a capital alphabet, that is q. Okay, and its sample value will be denoted by small q. So now either I can express this quantization error in terms of its sample value or in terms of random variable. That is why I have written here small q is equal to small m minus small v. Or I can express this quantization error in terms of random variable also. So that is capital Q is equal to capital M minus capital V. Okay. So with the input M, that is the random variable, right, having zero mean, and the quantizer is assumed to be symmetric. So it follows that the quantizer output, that's the random variable capital V, and therefore the quantization error Q will also have the zero mean, because input signal or input random variable is having a zero mean, even the output of the quantizer is also will be having a zero mean. So with this, the statistical characterization of the quantizer in terms of output signal to noise ratio, what we can do is we can find only the mean square value of the quantization error Q. Okay. So let us see how do we find the mean square value of the quantization error Q. So let us consider an input signal, that is a continuous time signal having an amplitude. It lies in the range from minus m max to plus m max. So this is a negative amplitude and this is a positive amplitude. Okay. So as we assume that the uniform quantizer is of a mid-rise type, okay, and we can say that the step size of the quantizer is given by, so delta is equal to 2 into m max divided by L. So m max is the peak amplitude of the input signal, right, divided by L. L is the what? Number of representation levels. Okay, to find the step size of the quantizer, so this is the formula. So which is equal to what? 2 times the maximum amplitude of the signal, okay, divided by number of representation levels. That will give you the expression for step size. Okay, so this is important expression which you need to understand also. There's so many problems they will ask you to find out what is the step size and all. They will give you the maximum amplitude of the input signal and they will also give you the number of representation levels. Then you should be able to find out what is the step size. Okay, so for uniform quantizer, the quantization error Q will have its sample values bounded by this value, that is minus delta by 2 plus delta by 2. Right? I said the maximum quantization error will be plus or minus delta by 2. Okay, so here if the step size delta, right? If the step size delta is very small or sufficiently small, then so when it can be small, when I have more number of quantization levels, right? Because delta is inversely proportional to the number of representation levels, L, right? If I increase the value of L, then the value of step size will be less. So with this expression only we can say, right? So the step size can be made small only when the number of representation levels are sufficiently large, right? So it is reasonable to assume that the quantization error Q, okay, is uniformly distributed random variable and interfering effect of the quantization noise on the quantizer input is similar to that of the thermal noise. So already I think we have discussed about thermal noise, right, in the third module. So you know what will be its mean and variance and other things. So we relate this quantization noise is also similar to the thermal noise. So now we can express the probability density function, that is PDF, of this quantization noise, okay, Q as follows. So that is FQ of Q is equal to, which is 1 by delta over the interval minus delta by 2 to delta by 2. Otherwise it will be 0. So graphically I can write like this. If I take, this is my sample value Q, okay. I think you can, yeah. So this diagram can be written. So this is the value of minus delta by 2 and this is the value of plus delta by 2 and its magnitude is 1 by delta. So this is my probability density function of the quantization error. Okay, so you can note down this. So this is, just I will show here like this. This is my plus delta by 2, this will be 0, right? And this will be my minus delta by 2. This is my sample value. Okay. So as I said, means so this is 1 by delta, right? This is my FQ of Q, that is the probability density function of the quantization error. Okay. So we must ensure that this incoming signal, okay, does not overload the quantizer to become this equation is true, right? So with the mean of the quantization error being 0 and what will be its variance, it will be, its variance will be same as the mean square value. So how do I find the mean square value? So that is sigma squared Q is equal to integral from minus delta by 2 to delta by 2 Q squared into FQ of Q into DQ. So this is the formula for finding the mean square error. Okay. Means if I know what is the expression for variance, I am saying the variance is the same as the mean square value. That is why I am writing sigma squared q is equal to integral from minus delta by 2 to delta by 2 q squared into f of q into dq. Okay, so that is the mean square error. So here q of q value will be what? It is 1 by delta over this interval, right? From minus delta by 2 to plus delta by 2. So that is why I am substituting that value here. So if I substitute that here, so I can write it as sigma squared q is equal to 1 by delta integral from minus delta by 2 to delta by 2 q squared into dq. So I hope you know what is the integral of q squared into dq, and you substitute the limits after integrating, and you will be able to get mean square value as delta squared by 2. So here one step you have to do integration of q squared into dq with limits what minus delta by 2 to delta by 2. So what value you are getting here after substituting the limits? Are you going to get the value of this mean square value as delta squared by 2? Just check and tell me. Yes, what is the integral of q squared into dq? Yes. Yes, what is the integral of q squared into dq?
Q cube by 3.
Pardon? Yes, what is its value?
Q to the power 3 divided by 3.
Yeah, q cube divided by 3, right? So you have to substitute in place of q as what? That is upper limit and minus lower limit. That is delta by 2. Okay, if you do that simplification, I hope you will be able to get this as delta squared by 12. Are you getting this? Just take 1 minute time, substitute and let me know. Are you getting this delta squared by 12 or not? And here 1 by delta is also there, right? 1 by delta into yes, is it possible to get delta squared by 12?
Yes, sir.
So the mean square value is what? Delta squared by 12, right? So that is nothing but the variance of the quantization error. Okay. So now what I was telling, L is the number of representation levels, right? So the L array number, okay, K, L array number K, denoting the kth representation level of the quantizer, is transmitted to the receiver in binary form. Okay. So if I denote R as what? The number of bits per sample. Means each level I am representing by some number of bits, right? So I am taking that in general as R. Okay, let R denote the number of bits per sample used in the construction of the binary code. Then I can relate number of bits used to represent per sample, right? And as well as the number of levels. So that is a relation. That is L is equal to 2 power R. What is this L? L is the number of quantization levels, right? And what is this R? R is the number of bits used to represent each level. Okay. Yes, is this clear formula? L is equal to 2 power R. Maybe textbook to textbook, the variations are, means the notations will be different. So you don't have to worry. This is from your prescribed textbook only. So where I'm saying L is the number of quantization levels. R is, that capital R is what? The number of bits used to represent each quantization level. Okay, means if I am using 2 bits per sample, then how many levels I can have? So L is equal to 2 power 2, right? So I can have 4 different levels. Isn't it? Getting my point? If I am representing each sample by 2 bits, then I can have what? 4 levels. That is 0, 0, 0, 1, 1, 0, and 1, 1. That's what is the number of representation levels. And we can write like this also, right? R is equal to log L with base 2. by taking logarithm. Okay. Then I am going to substitute the step size formula. What is the step size? I wrote in the previous slide, delta is equal to what? This one, right? 2 max, 2 into maximum input of the amplitude of the input signal divided by L, right? Now I know what is L. L is equal to 2 power R. So I'm going to substitute that value here, and I can relate the number of bits used to represent each quantization level and as well as step size and the number of levels also. Okay, so delta is equal to, so here I'm substituting the value of L as 2 power R in this equation. Okay, then this is my expression for delta, right? Just now I found what is the mean quantization error, that is sigma squared q, right, which is equal to delta squared by 12. In the previous slide it is there, right? So sigma squared q is equal to what? Delta squared by 12. So let me substitute delta as that value. I substitute delta as 2 into maximum peak amplitude of the signal into 2 power R. I will get this expression. Am I getting this equation or not? So here, if I substitute delta as 2 max divided by 2 power R in this equation, right, delta squared by 12, then I can write sigma squared q is equal to 1 by 3 into m squared max into 2 power minus 2R. Just substitute and you divide by that number. See, 2 squared is 4, 4 ones are 4, 3 is 12, right? I hope you will be able to do that simple mathematics. So 1 by 3 into m squared max divided by 2 power 2R will be there. Since I'm writing it in the numerator only, I can write it as 2 power minus 2R. Yes, this is the expression for what? Mean quantization error, sigma squared q. Okay, so now if I denote the average power of the message signal m of t by a letter p, okay, if I denote the average power of the message signal m of t by a letter p, then I can express the output signal to noise ratio of this uniform quantizer as output SNR is equal to what? This is the signal power, right? And this is the noise power, P by sigma squared Q. So just I'm substituting the value of sigma squared Q in this expression. So which is nothing but what? Is what I get. So 3P divided by m squared max into 2 power 2R. So this is the expression for output SNR of the uniform quantizer. What is that? 3 into the average power of the message signal divided by square of the peak amplitude of the message signal into 2 power 2 into R, where R is the number of bits used to represent each sample. Yes, hope this point is clear. Yes, any doubts in this so far, whatever I was discussed about finding the output SNR of the uniform quantizer? So this expression has been asked many times. For 8 marks they ask. Okay, derive an expression for output signal to noise ratio of a uniform quantizer. But this is what you are supposed to prove. Output SNR is equal to 3P divided by m squared max into 2 power 2R. So from where you have to start? You have to start from the beginning, that is from this point. From this point you have to start. Let quantizer input be the m sample value with the 0 mean and its random variable m and so on. Okay. So just, and you should know how to find this probability density function of the quantization error. Then you will get that expression. Then you can substitute what is output SNR. Fine. So many things are there here. I told what is the expression for step size, and I have told what is the expression for the number of quantization levels, that is L is equal to 2 power R, right? And then this is the expression for output SNR. Okay, so the equation means 7.44 is this one only, right? The expression for output SNR, right? So shows that the output SNR of the quantizer increases exponentially with increasing number of bits per sample. Right, output SNR is equal to what I get? 3p divided by m squared max into 2 power 2r, right? So with this, what I can say is the output SNR of the quantizer increases exponentially with increasing number of bits per sample r, isn't it? Because it is directly proportional to square of this output SNR 2 power 2r. Then increases exponentially with the number of bits used to represent each sample. So an increase in R, right, requires a proportionate increase in the channel bandwidth. So what I mean to say is, if I increase the number of bits used to represent each sample value, I said the quantization means output SNR will also increases exponentially. But with that, I need more bandwidth, right? Increasing the value of R will also proportionately increases the channel transmission bandwidth. So with that, we see that the binary code for the representation of the message signal, which we use in pulse code modulation, provides the more efficient method. Okay, because the value of R will be the binary code, right? So with that, what we can say is the binary code for the representation of the message signal provides a more efficient method for representing the message number of quantitation levels and even representing the digital pulse in terms of numbers, digits, zeros and ones. So, okay, let us take this problem. Have a note of this. So far, whatever I derived expression for output SNR, then quantization noise and all, it is in general. Okay, we have not taken any specific value of the message signal amplitude or other things. So here it is taken with respect to some value. So let us consider a sinusoidal modulating signal of amplitude AM. Okay, so that will utilize the representation levels provided. So the average signal power, as I said, by assuming a load resistance of 1 ohm, I can write it as P, right? That is the average power of the message signal I used to write, right? So here, by considering a modulating signal, right, with the amplitude AM, its average power will be A squared M by 2. So this we know very well, right? The average power of the message signal with an amplitude AM will be what? A squared M by 2. Then the total range of the quantizer input will be what? 2 times the maximum amplitude of the message signal, that is 2 AM. Since here the modulating signal swings between minus AM to plus AM. See, minus AM is the negative peak amplitude and plus AM is the positive peak amplitude of the message signal. We can set M max is equal to AM. Right? M max is equal to AM. So if I substitute that value here in the expression of quantization noise, wherever M max was there, I can replace that M max by A suffix M as the peak amplitude of the message signal. So with that, I can write the quantization noise, that is sigma squared Q is equal to 1 by 3 into A squared M into 2 power minus 2R. Okay. So with respect to that, I can write the output SNR expression for the uniform quantizer. Okay, is what output SNR is equal to. So this was the general expression, right? 3P divided by M squared max into 2 power 2R. So wherever M max is there, I need to substitute M max by A suffix M. And wherever P is there, I need to substitute P by A squared M by 2. Right? By substituting those values, I can say what is the output SNR for the uniform quantizer with a sinusoidal modulating signal. So that is what is done here. So instead of P, we have substituted A squared M by 2. and a squared m and 2 power minus 2r by 3, right? So which is equal to what I can write? So a squared m will get cancelled. I can write it as 3 by 2 into 2 power 2r. So this is the expression what I get for output SNR of the uniform quantizer for a message signal having an amplitude of a suffix m. Okay. So then I can express this is in terms of ratio. I can express this output SNR in terms of dB also, right? By taking logarithm of this. So if I take the log of this, what I get? So by taking logarithm on both the sides, so 10 log of output SNR with base 10 is equal to, so log m into n, it will be what it will get? Log of mn. Yes, what is the value of log of 3 by 2 with base 10? That will be 1.8. Okay. Then just see this 2 power 2r is there, right? So what is the value of that, logarithm of that? So that give you 6r. So in terms of decibels, what I can say is the output SNR will be equal to 1.8 plus 6r. Means, so where r is the what? Number of bits used to represent each sample, right? Number of bits per sample it is, right? So 1.8 plus that. So it depends, means every bit will add so much of dB to the SNR. So here this table gives you for different values of L and what is the number of bits per sample I use and what is the SNR in dB. Okay. So if I use R is equal to 5, right? So L is equal to what? 2 power R, right? So 2 power 5 is equal to 32. And if I substitute R as 5 in this expression, and you may get the signal to noise ratio in dB as this much, 31.8 dB. Okay. So similarly, if I use 6 bits per sample, that is R is equal to 6, then L is equal to what? 2 power 6 is 64. Then this is the dB I get, 37.8 dB. And if I use 7 bits per sample, then 2 power 7 is 128. With that, the output SNR in dB will be 43.8 dB. Then if I use 8 bits per sample, then 2 power 8 will be 256. Then the output SNR will be 49.8 dB. Okay. So if I know how many number of bits I use per sample, I will be able to calculate the number of quantization levels, and then I will be able to say what is the output SNR. So this is asked so many times in the exam. Okay, so be thorough with this derivation. Yes, any questions to ask with respect to this derivation? So this is the output SNR expression for uniform quantizer when the input signal is a sinusoidal modulating signal having a peak amplitude a suffix m. Yes, any questions? No questions? Yes, you people don't have questions. Shall I go to the next one? Yes, Sanket. Sanket. Gautam Hegde. Gautam Hegde. Yes, answer attendance. Nagavini. Gautam Hegde. Why you are putting message man Gautam Hegde? So your speaker is not working, right? Yes, Nagaveni, why you are not talking? Nagaveni. Yes, Aditi. Akshay. Akshay.
Yes, sir. Yes, sir.
Ananda.
Yes, sir.
ಹೇಳು ಆನಂದ್, how L and R related?
Sir.
ಆ ರಿಲೇಷನ್ ಹೇಳಿದ್ರೆ ಅಟೆಂಡೆನ್ಸ್ ಕೊಡ್ತೀನಿ. How L and R related?
Sir, inversely proportional.
ಏನ್ ಇನ್ವರ್ಸ್ಲಿ ಪ್ರೊಫೆಷನಲ್ ಬದನೆಕಾಯಿ? L is equal to what, man?
ಈಕ್ವೇಶನ್ ಹೇಳ್ಬೇಕಾ ಸರ್?
ಈಕ್ವೇಶನ್ ಹೇಳ ಮತ್ತೆ. ಹೆಂಗ್ ರಿಲೇಷನ್ ಅಂದ್ರೆ ಏನೇನ್ ಹೇಳ್ತೀಯ?
ಓಕೆ.
ಏನ್ ಕೇಳಲ್ಲ ಅನ್ಸುತ್ತ ನೀವು ಪಾಠನ ಅಲ್ವಾ? ಸುಮ್ಮನೆ ಲಾಗಿನ್ ಆಗೋದು. ಅಟ್ಲೀಸ್ಟ್ ನೀನಾದ್ರೆ ಆಕ್ಟಿವ್ ಇರ್ತೀಯ ಅಂದ್ರೆ ನೀನು ಕೇಳ್ತಾ ಇಲ್ಲ ಅನ್ಸುತ್ತ.
ಸರ್, L is equal to 2 power R.
L equal to 2 power R. ನೀನ್ ನೋಡ್ಕೊಂಡ ಬರ್ಕೊಂಡಿದ್ಯಾ? ಏನ್ ಮಾಡಿದ್ಯಾ?
ಅದೇ ಸರ್ ಬರ್ಕೊಂಡಿದ್ದೆ, ಅದು ಲಾಗ್ ಪವರ್ R ಅಂತ ಅನ್ಕೊಂಡೆ, ಆಮೇಲೆ 2 ಪವರ್.
ಓಕೆ, ಸೊ L is equal to 2 power R. L ಏನು R ಏನು? What is L and what is R, man?
ಸರ್, L ಅಂದ್ರೆ ಲೆವೆಲ್ಸ್ ಸರ್. ಲೆವೆಲ್ಸ್.
Number of representation levels. Okay,
R ಅಂದ್ರೆ ಬಿಟ್ಸ್, ನಂಬರ್ ಆಫ್ ಬಿಟ್ಸ್.
Number of bits used to represent those levels. ಅಲ್ವಾ? Okay. ಅನಂತ. ಅನಂತ ಏನು ಮೆಡಿಟೇಷನ್ ಮಾಡ್ತಿದ್ದಾನೇನಾ? ಆನಂದ. Ashwini.
Present, sir.
Yeah, tell me the expression for step size. What is the expression I can write for step size? What? Delta. ನೀವು ಆನ್ಸರ್ ಹೇಳಿದ್ರೆ ಅಟೆಂಡೆನ್ಸ್, ಇಲ್ಲ ಅಂದ್ರೆ ಇಲ್ಲ. ಸೃಜನ್.
Yes, sir.
What is the expression for output SNR, man?
Sir, 2 max by R.
Yeah, 2 max by
R.
R. How it can be 2 max by R, man? Delta.
Sir, 2 power R.
2 power R. Or you can say L.
Yes.
Right? 2 into maximum amplitude of the input signal divided by L. So where I said L is equal to 2 power R. Okay. What about Srujan?
Yes, sir.
Expression for output SNR.
Sir,
Yes.
3p by m square max.
Yeah, 3p by m squared max into
2 power R.
2 power R. Is it 2 power minus 2R or 2 power ಏನು? Incomplete. Yes, Bharati.
Yes, sir.
Bharti, can you tell what is the expression for mean quantization error? That is sigma squared Q. Sigma squared capital Q. Quickly, Bharti. Otherwise, I put
Yes,
object.
sir.
Huh? See, if you are not noting the equations, ಒಂದೊಂದು ಈಕ್ವೇಶನ್ 4 ಸರ್ತಿ ಹೇಳ್ತಾ ಇದ್ದೀನಿ, ಏನು ಬರ್ಕೊಳಲ್ಲ, ಏನ್ ಮಾಡ್ತೀರಾ ಮತ್ತೆ? Bharti, simply logging in and that's all, doing something else. Do you think that it will help?
No, sir, I'm not, just going through pages.
No, at least
So
if
I
you have
got it, sir.
noted, you could have told now by seeing sigma squared Q. I said it is an important derivation. Every time they ask, already the model question paper have been released. Do you know that? On
Yes,
the
sir.
ETU
One,
website, it is there available. You just download and see. Huh?
yes,
Is
sir.
Chandan K? Chandan K is not there. Is Chandana?
Yes, sir.
Chandrika? Chandrika? Ramsai? Dhanya?
Yes, sir.
Yes, why my also didn't respond? Can you tell what is the output expression, means output SNR? When I consider the message signal is a modulating signal with an amplitude of A suffix M. By considering the message signal with an amplitude of A suffix M, what will be the expression for output SNR in terms of dB you tell? In terms of dB. In terms of dB, the final expression what I said just now. So I told the table also for different values of R. It is 1.8 plus 6R, no?
Oh, yes, sir.
God only knows what you people will be keep doing. So exam ಬರೆದ್ಮೇಲೆ ಗೊತ್ತಾಗುತ್ತೆ ನಿಮ್ಗೆ ವಿಡಿಯೋ. Girish,
Yes,
what is the expression for output SNR, man, in terms of dB? Girish.
yes, sir.
So absent ಆಗ್ತೀನಿ ನಾನು ಮಾತಾಡ್ತಾ ಹೋದ್ರೆ. Hima, there is no point in giving attendance. Hima?
Yes, sir. Yes, sir.
Yes, sir.
Yeah, can you tell the expression for output SNR in terms of dB?
Yes, square M.
In terms of dB, man.
1.8 plus
1.8 plus
6R.
6R. Yes, what about Hima?
So 1.8 plus 6R.
1.8 plus 6R. What is that R, man? Yes, what is that R?
Bits, sir.
Bits per sample.
Yes, sir.
How it is related to number of quantization levels?
2 per R.
2 power R. Okay. And Sagar? Sagar. Skanda?
Present, sir.
Bhargav?
Yes, sir.
Bhargav, can you tell the expression for mean quantization error, man? Mean quantization error. If you are not telling the answer, I will put object, man. Bhargav. Mean quantization error. It is so difficult, huh? Okay, Karunya.
Yes, sir.
Yeah, can you tell the expression for mean quantization error? Karunya.
I don't know, sir. I didn't note down.
But why people log in and stay like this?
I was listening, so I didn't note down.
Why you didn't note down? You should note down, no? So the derivations, right? Okay, can you tell me the expression for output SNR in terms of ratio, not in terms of dB? Yes, in terms of ratio. See, 3 by 2 into 2 power 2 R, no?
Delta
Huh?
square by 12, sir.
No, no. 3 by 2 into 2 power 2 R. That is in terms of ratio, what we can say. If I take log of that, 10 log of that, I will get in terms of dB as 1.8 plus 6R. Yes, Kuber? Leah? Manasa?
Yes, sir.
Manasa SH? Manasa SH? Manish? Manjunath?
Yes, sir.
Manjunath, can you tell the expression for step size man?
Step size, sir. L is
Delta.
equals to L is equals to 2 power R.
Okay, L is not step size man, delta is step size. L is number of quantization levels.
Sir, delta is equals to 2 m max by 2 power R.
Yes, Manoj?
Yes, sir.
Yeah, can you tell the expression for number of quantization levels? Number of quantization levels, man. L is equal to what? L is equal to what, man? Expression L is equal to how it is related to number of bits. So no idea. Manusri?
Present, sir.
2 raised to
Yeah.
R, sir.
Yeah, can you tell me the relationship between number of quantization levels and number of bits used to represent each level?
So L is equal to 2R. 2 power R.
L is equal to 2 power R. Okay. Yes, Mohammed?
Present, sir.
Yeah, can you define quantization, man? Mohammed? Mohammed?
Yes, sir.
Yeah, how do you define quantization?
Don't know, sir.
Quantization, man. Why you're Googling?
No, sir.
With the diagram I have shown, no, man. With sampling, what will happen? With quantization, what will happen? Huh?
Yeah.
Yes, is it possible to say?
No, sir.
No, you can't. What, man? Discretization of the amplitude of the sampled signal is the quantization.
Standardization of the
I feel
count.
shame, man. After saying all this 2 hours, still you can't define what is quantization. You are saying no.
Yes,
So it is not
sir.
reaching. Be attentive, man. Try to learn. See, learning is learner's responsibility. Only teachers
sir.
should not pressurize. You should feel that you have the responsibility in learning. Okay?
Okay, sir.
Mohan Sai?
Yes, sir.
Yeah. Can you define sampling? Sai, Mohan Sai. Sampling, man, simple definition. You can't define sampling? What is this, man? You're studying in DSP, you're studying in other semester also. This semester also I'm teaching, I thought also many times. So doing sampling, you're going to discretize the signal in time. Isn't it? At a discrete instance of time, you'll get the samples. That is what the
So
sampling process is.
discrete of analog signal in time is called sampling,
Sampling.
sir.
Okay, you are saying definition. Okay. Namita,
Yes, sir.
can you tell the expression for output SNR in dB?
3 by 2. No, sir. In dB, like it will be 1.8 plus 6R.
Okay, fine. Yes, Noreen,
Yes, sir.
Neeraj,
Yes, sir.
Niharika. Yes, Niharika. Nishchit Jain,
Yes, sir.
Pooja,
Present, sir.
Prajwal, Prithvi,
Present, sir.
Rakshita,
Present, sir.
Rakshita K,
Present, sir.
Ramya, Rishav, Rishav. Yes, Ramya is there. Ramya, Rishav, Rohit Joshi.
Yes, sir.
So present,
Sir, Rohit present.
Rohit, can you tell me the expression for number of quantization levels, man?
Sir, 1.8 plus 6R.
What, man? I'm asking number of quantization levels. That is output SNR in dB, what you are saying. L is equal to what I'm asking.
Sir, L is equals to 2 power R.
Okay, man. Okay. Rushank?
Present, sir.
Yeah, what about you, man? Can you say what is the expression for quantization error? Mean quantization error?
You're asking me, sir?
Ah, great,
I
you're
don't know,
talking
sir.
now today. Yeah, Rushank.
Yes, sir.
Do you remember or not?
No, sir.
So I got something delta
2 power
squared
R,
by
2 power
12.
R.
Delta
2
squared
power
by
R,
12
sir.
is what, man?
2 power R.
No. Delta squared by 12 is the mean square quantization error, man. Okay, very simple. Delta squared by 12, where delta is the step size. Okay, Gayatri,
Present, sir.
Harshita,
Present, sir.
Sachin,
Yes, sir.
Sanket, Suresh,
Present, sir.
Siddharth,
Yes, sir.
Souvik Rai.
Yes, sir.
Yeah, what about you, man? Can you tell me the expression for step size? Step size, man. Delta. Yes, quickly you should define what is delta. Yes, Subiksha.
present, sir.
Ipana,
Present, sir.
Vishal,
Present, sir.
Vadva,
Yes, sir.
Danish. Yes, Danish. Abhishek Reddy. Gautam, Nagveni.
Yes, sir.
ನೋಡಿ ನಾಗವೇಣಿ ಈಗ ಎಸ್ ಅಂತೀರಾ
Sir?
ಎಸ್
Sir, Prajwal present, sir.
ಓಕೆ ಯು ರಿಯಲೈಸ್ ನೌ 10:33.
So, D sir also present.